The time is now 11:30 a.m. Welcome to SRIL Robotics Innovation Lab, workshop number 1. My name is Clement, and on behalf of our entire team, thank you for joining us today. I'd like to begin by acknowledging that this presentation is being transmitted from Surrey, British Columbia, Canada, on the traditional, unceded territories of the Coast Salish peoples. For the comfort and enjoyment of everyone here, I would like to remind everyone to please turn their microphone and camera off for the duration of this presentation. We hope you enjoy the UAV Mechatronics workshop.
Hi everyone, my name is Daniel. So on the screen right now, we have a rough plan for today's workshop. We'll start with an introduction to our organization, SRIL Robotics Innovation Lab, and then we'll introduce our speaker and hand it over to him for his presentation. And finally, we will end with a Q&A session.
Hi everyone, I'm Sophie and I am SRIL's president. SRIL is dedicated to empowering high school and university students in robotics and STEM. In addition to hosting this summer workshop series, we will also develop a wide range of programs and resources. You can check out the resources and opportunities on our website, and starting from August 1st, tune in to our YouTube channel. Today's workshop will be led by Raymond Yu. Raymond is a recent UBC mechanical engineering graduate specializing in mechatronics. He was the captain of the UAV student design team, developing several innovative ground and airborne systems. He had several co-ops ranging from local tech startups to Airbus, where he worked on data analytics, controls optimization, flight test instrumentation, and rapid prototype development of various aircraft systems. Let's give a warm welcome for Raymond.
Oh, great. Well, thanks for the introduction. Let me share my screen and I'll start the presentation. All right, can everyone see my screen? Thumbs up for if you can see my screen. Thumbs up, wonderful. All right, full screen. Well, thank you, Sophie. As she mentioned, my name is Raymond. I'll be leading today's workshop on mechatronics engineering and its application to UAVs. So a brief overview. At high level, well, I'll introduce the topic and then I'll try to define what it means to be a mechatronics engineer, what mechatronics engineering is. And through that, we'll be using 2 case studies to explore it in detail, a drone developed by one of my former student design teams, as well as a larger drone I developed during my time at Airbus. Then we will conclude the presentation with a little live Q&A. And we should be having at least 10-15 minutes for the live Q&A. And I'll note that I've been told that the audience ranges from, for example, high school all the way up to first, second, third, maybe even fourth year university. So it's a bit of a challenge to have sufficient breadth to engage all of you at once. Some things might be a bit simple, some things might be a bit too complex, but save your questions to the end. There'll be multiple opportunities to ask them. Right, so the introduction, I want to address these questions throughout my workshop. And well, starting off with who am I? What is a mechatronics engineer? What does a mechatronics engineer do? And how is this relevant to small aircraft like UAVs? And how can you start? Oh, the guy in the picture, that's me. And as Sophie mentioned, I'm a recent UBC engineering grad, just a few months ago, actually. I graduated from the mechanical engineering department, but specializing in mechatronics engineering. Yeah, and also as Sophie mentioned, I spent multiple years on the drone student design team, where I gained invaluable experiences of developing both ground and airborne systems, as well as various supporting systems for the UAVs. And I have more than 2 years working in the aerospace industry, ranging from local companies like Cascade Aerospace out in Abbotsford to the multinational Airbus over in Europe. And I'm also currently working as some form of systems architect in the same industry. Now, what is a mechatronics engineer? Well, I'm not trying to intentionally steal a definition from the program out at UBC or SFU. This would be in my words, hopefully though my definition and their definitions are also aligned. So the word mechatronics, well, that comes from the union of mechanical, electrical, software, and controls engineering. If we start off with the mechanical system, we know that force, mass times acceleration, and then conversely, torque is inertia times angular acceleration. And an example of that would be a motor, whether it be an electric car, a drone, or like a garage door opener. And the electrical component, we all hopefully have seen an equation, D equals current times resistance. A good example of something which uses that equation would be a battery or a power system. And in terms of software, we've all seen a bit of software code before. It could be as simple as like Arduino code, or it could be as complex as machine vision. And finally, the last part of mechatronics engineering would be the controls aspect. And you can see here, there's a little feedback loop. And a prime example of a controls engineering problem will be an autopilot system, whether it be for an aircraft, a ship, or a self-driving vehicle. And this is a mechatronics is very multidisciplinary, incorporating aspects from all these different subsets. And that leads me to my definition. So a mechatronics engineer works at the interface between hardware and software systems, or essentially anything with moving parts that requires power. Now, reiterating the definition, there's many different applications ranging from automated manufacturing lines. So we can see a multi-arm robot over there where you supply power to the motors then turn the mechanical fixture so that the end of the arm reaches one point in 3D space while not overshooting, reaching that exact point using a controls algorithm. And another application would be like self-driving vehicles, taking data from various sensors, be it a GPS or like a computer vision camera, and then actuating the wheels, turning the wheels, or applying braking force. And a further extension, also spacecraft or aircraft, which I'm most interested in. For example, the autopilot system of an aircraft is very much a mechatronics problem, trying to maintain level flight, even in adverse weather conditions, to ensure that all the passengers on board have a pleasant experience. Now, I do have a little asterisk next to the application. So because even though my definition is anything with moving parts that requires power is mechatronics engineering, that doesn't mean that you can't specialize in a particular field of it, because mechatronics engineering offers great foundation in various of these technological disciplines. And how can you start yourself? Well, all these things have one thing in common. You can all start learning or experiencing what it's like to be exposed to mechatronics engineering by just having like a little Arduino project, driving a motor, perhaps holding a position, getting user feedback so that you can all experience this at home. Now, this would be the first case study which we're going to explore. And a little shout out to the UBC Unmanned Aircraft Systems student design team for providing these lovely graphics, and also providing me the invaluable experiences which allowed me to succeed today. Now, first off, what is a drone? Well, definition's over there, but the US Federal Aviation Administration defines a drone as a powered unmanned aerial vehicle that can fly either remotely or be flown autonomously and can also carry a payload. So they can range from very large fixed wing drones, be weaponized like you see on the left. They can also be little hobby grade RC aircraft you see in the center. And they can also be the very ubiquitous and widely proliferated DJI drone products you see on the right-hand side. So in this particular case study, we're going to be exploring a drone that's the size of the DJI product on the right-hand side. And in the subsequent case study, we're going to be exploring a slightly larger drone in between the size of the center and the left-hand drones. So this is a drone in question. that we're going to be exploring. This is a custom designed, custom built quadcopter with around 25 minutes flight time with a maximum takeoff weight around 5 kilos. It's a very robust engineering tool. So let's continue with the drone architecture. So you can see many different components the drones comprised of many different components, but at the heart of every drone is a flight controller, which is that orange thing labeled cube. And that's the brains of the drone. All the sensors, all the motors, any peripheral all reach that at one point or another. Then towards the left, we have the payload. Oftentimes it's a camera, but it could also be a smaller unmanned ground vehicle. It could be a package to deliver various different applications. And then towards the bottom, we have the motor and motor controller, which provide the lift and power required for the drone to lift off. Have a power distribution board separating the power from the energy from the battery to feed into both the motors and all the other peripherals like the flight controller or the payload, for example. And then towards the top right, we have the range of sensors and telemetry systems which allow the drone to know or to sense, to feel, to hear, to know where it is in 3D space in order for it to complete its mission. Now, bringing it back to this drone over here, we can see that the architecture is labeled. And towards the center of the drone, we see the flight controller slightly hidden by a boom. We see the motors and motor controller at the end of the boom and within the frame. We have a payload of a camera in this case. We also have a battery, which is a nice big heavy brick, in addition to a power distribution board above it. And we also have the telemetry and sensor suite. And in case you guessed, the sensor right to the top of the drone is the global positioning system. Now we're going to be I'm going to be emphasizing the flight controller, the propulsion system, which comprises of the motor and motor controller, as well as the sensor, the navigation suite of the drone. All right, so this is the flight controller. Well, without a flight controller, the drone would likely crash. So it's a very key part of the aircraft. And like I said, it is the brains of the aircraft. Any commands, any user inputs, it's all handled by this little computer on board. And actually, here's some code extracted straight from the open source autopilot code. And if we focus our attention to the bottom right, we can see a little feedback loop. What you see here is a PID controller. So it's a very simple and popular control algorithm used for these kinds of drones and other linear systems. They react to various sensor or environmental inputs. It's used for stabilization and control. We can see at the output of the little PID controller, we have the actuators, which are the motors of the drone. And then the actuators allow the quadcopter to move around, to navigate in 3D space. And then we have a feedback loop with the various sensors on board. And this loop runs continuously with the control algorithm to maintain steady flight or desired flight characteristics. Now, a little example. So say we have our drone traveling in a straight line here, and that is the expected path if we tell it to move in a straight line in that direction. But what happens if there's wind? It's gonna get blown off course. Now, without a feedback loop or without a well-designed controller, the drone, well, it could fly off, go haywire, it could possibly crash. But with a well-designed, well-tuned control system within the flight controller, we can see that hopefully it would deviate only a little bit, but return onto its original path. And I'll talk a little bit more about this feedback loop. So we have a command which is sent to the drone. We have a target angle that we want to proceed, which is due east in this case. We're subtracting the feedback, which I'll explain later. So we'll begin air, which we feed into the control system. And that control system then commands the different motors to actually rotate at different RPMs, taking into account the wind disturbance, and then feeding into the drone, the physical drone model, which responds to all these commands. And then we have received the feedback from it, from a compass, for example, and that gets subtracted from our target command, and this runs repeatedly. Now, if we see a little graph here, we can see that desired or probably ideal response would be that if there's an external perturbation, the trajectory of the drone would deviate a little bit, but it would compensate itself due to this feedback loop. So it would eventually reach a steady state level flight path. However, there are differences in this. For example, if the controller is not designed well, perhaps the drone would oscillate back and forth repeatedly. And obviously this is not a desired solution. And what's more, it can also be, the solution can diverge. So if the controller is designed poorly, if the drone is inherently unstable without a feedback loop, then any minor deviation would propagate, become bigger, 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 and bigger until the drone either self-destructs or crashes. Right, now we'll be talking about the motor and the motor controller. So a motor is a definition of a mechatronic system because you're converting electrical to mechanical rotational energy, and then that's controlled via more electronics and software. So often the motors used in these types of drones are three-phase brushless DC motors. Three-phase just means there's 3 wires entering each one of these motors, and then there's different sets of coils which get energized, a magnetic field is generated, and the permanent magnet inside the rotor then rotates as a response to the magnetic fields. And we can see that even on drones like this, you can see the 3 wires, one for each phase of the motor. And I'll explain a bit more about the motor controller in detail on the next slide. So this looks a bit complicated, but I'll explain it. So I mentioned there's 3 phases or 3 wires feeding into the motor. One of these graphs represents the signal coming out of each one of these wires. They're 120 degrees out of phase, so that there's a peak, and then 120 degrees later, there's another peak, 120 degrees later, another peak, and then before repeating back to the original peak. And this allows the motor to receive the very optimal amount of both performance and power received to enable lift generation by the motor. And we have the controller, a high-level schematic of a controller on the right-hand side. So the MCU is a little controller, almost like the flight controller, but just for the motors. The controller, the MCU, sends out a signal, sends out one of these little signals to a driver. The driver then amplifies that signal, provides more power, more voltage, more current to it, so it can actually be fed to the motor. We have different switches here, which allow the signal to go from positive to negative. And that switching sequence then energizes the coils of the motor, thus spinning the motor, the rotor, which comprises of permanent magnets. And we also have a feedback loop here from Hall effect sensors, which detect the magnetic field of the motor, of the rotor. And that signal gets fed back into the controller, and the signal gets continued on in this feedback loop. All right, and the next part I will explain will be the sensors. So there's many different types of sensors on board the drone, from a compass to a voltmeter to measure voltage to a pitot tube for airspeed. And these sensors can vary a lot in size. So for example, an accelerometer, which detects acceleration, which is that little black square out there, it's only a few millimeters by a few millimeters. This GPS unit here is probably the size of a loonie or toonie. And we also have a pitot tube down here, which measures airspeed. Airflow goes in, take a pressure differential using that chip over there, so you can have relative airspeed. And then we can see here some of the code which is in the flight controller. It does reference each one of these sensors. And in terms of guidance and navigation, if we imagine that we have our drone here, it's delivering a little package. If it's flying through, say, a very built-up urban area, say between buildings, perhaps we would lose some of that sensor data because of interference. Or a way to resolve this issue would be to take the data from previous positions where you still had accurate sensor data, and instead have an optimal state estimate. So this little orange line here represents a current measurement, but it could be very noisy. or it could be missing data from some sensor sources. But this is what your predicted estimate that the flight controller would estimate based on other sensors. And then you have some average or weighting algorithm to determine the optimal state between what you actually measured versus what you predicted from past events, so that you can still navigate even in like a GPS denied environment. And this type of a sensor fusion algorithm can be called the Kalman filter. And that Kalman filter can also filter out noise in real time as well, so you can get better sensor data for your flight controller. Now, this concludes the first case study. On to the next one. Right, now I'll also try to connect how the skills of a mechatronics engineer helped here. Brief disclaimer, everything that, especially everything that I say or show in this part of the case study or presentation is taken from a public source where I have authorization to use it. And so this AlbatrossONE drone, it's technically a drone, it's a fixed wing drone, and it's a 20:1 scale demonstrator with very long wings. The alternative to making a scale demonstrator of this size would be to modify like $100 million flight test aircraft. So by building a drone of this size to test the technology, it's both a cheap and low risk way to extract data from this new technology. And I'll give a little background on what the problem that it's trying to address. So on aircraft, usually the longer that your wings are, the more efficient they are, the less drag you produce. So for example, this glider here has a very long wingspan. However, having a longer wingspan also means that you have more lift generated along the wing. And that means that you also have a bending moment or torque around the wing root and throughout the wing. So sure, you want a longer wingspan because you get a better efficiency, but you also need a heavier wing to prevent it from snapping under different environments. And what's more, a longer wingspan also means that you can't fit into airports as well, which is why the 777X here has folding wingtips. So in conclusion, you want longer wings because it gives you a better aerodynamic efficiency. But the downside of that is that you need heavier wings to reinforce the wings to prevent them from snapping, for example. And the longer wings also means that you're limited in the amount of airports that you can fly to. So what is a solution? A solution is the SEMI-AEROELASTIC hinge as demonstrated by the AlbatrossONE. So you can see here that even if there's a gust along the wing, and this wing is actually quite long compared to the actual aircraft it was scaled off of. So instead of the energy being transmitted along the wing, that energy is being used to bend the wingtips so that you won't need as many structural reinforcements along the wing. So you get the benefits and advantages of a very long wing without the additional weight penalties. So within the AlbatrossONE, there's a large assortment of different sensors and instrumentation systems on board. So I recall, or I hope that I mentioned that sensors are a very important part of mechatronic systems. So within the AlbatrossONE, I was one of the lead designers of its flight test instrumentation system. So incorporating all these sensors and more into the aircraft so that we can get actionable data from its flight test campaign. So we can see the position of some of the sensors on board the aircraft, got camera on the tail. We have a voltmeter and ammeter to measure the power being delivered to the engines. We have the GPS, barometer, compass, etc., and a flight controller within the fuselage of the aircraft. We also have various air data sensors in the nose and many other sensors which can be seen from this view. And as one of the lead designers of its FTI system, I'm responsible for selecting the sensors, building the wiring harnesses, programming the microcontroller, characterizing the antennas, coding different scripts to retrieve the data from the sensors, as well as post-processing the data. And with regards to the flight data recorder, which I helped design, disclaimer again, all the pictures that you see here are from the internet or from other personal projects. They're not actually from the AlbatrossONE, but within or on board the aircraft, there is a similar setup. So we can see here, we have a flight data recorder with different sensor inputs, whether it be for angle of attack or for airspeed. And then we have a printed circuit board here, which we can compress large circuit boards. And some of my roles was to design the printed circuit board for the flight data recorder, as well as to say use an oscilloscope to verify the integrity of the different signals, as well to, for example, shield and to mitigate electromagnetic interference effects, and to ensure that all the sensor data had very positive, clean readings. And as an extension of my work, for each flight test campaign, there could have been tens of thousands or hundreds of thousands of data points. So a lot of what I've done was data processing or data analytics. And you can see here, these pictures are from other personal projects, but we can see, like, for example, a flight path of a fixed wing drone. Something similar happened with the AlbatrossONE as well. And then there's different signal readings, as some of them could be noisier than the others. So we had to filter some of the data to determine the conclusions. And then as well, I also supported a lot of the flight test activities on the flight line as well. So you can see here, I'm running diagnostics and troubleshooting possible issues with the aircraft on the flight line during a lull between flight test campaigns. So here's a pretty picture of the AlbatrossONE in the air over the English countryside. This is a screen capture from YouTube. I'll share the link later if you're interested in seeing the promo video. But sensors and instrumentation is a key part of mechatronics engineering. This definitely enabled me to succeed with the flight test instrumentation system of this aircraft. Even though it wasn't directly mechatronics engineering, it was the foundation that mechatronics engineering provided me, enabled me to work well with these electronics and sensor suites. And this concludes the case study. Right, now I will wrap up this presentation. So as a recap, some of the architecture on board the drone, the importance of its flight controller, its motor controller, as well as various sensors and guidance and navigation systems on board. Then we talked about the AlbatrossONE, its technology, the problem it's trying to address, as well as my role within the project, and how working with sensors, electronics, and instrumentation systems assisted me and enabled me to succeed. Now, a few closing remarks. Well, reminding everyone that mechatronics is a combination or union between mechanical, electrical, software, and controls engineering. You get to work at the interface between hardware and software systems. And I personally think it's very, very relevant in today's digital and connected applications. So not only are there engineer roles, you can also, for example, work as a data scientist or as a flight test engineer in other domains. And you guys can all sample mechatronics engineer yourself as long as you grab an Arduino kit and a motor and you just try controlling the motor. And I think it's a great way to lead into what it feels like to be a mechatronics engineer. And here are some of the resource links. As I promised, I believe that these links will be shared with all of you guys later at some point. We go next. And this actually concludes my presentation. And we will now move into the live Q&A. So if you go to menti.com, enter code A74430, you can ask all the questions you want, and I'll do my best to address all of them. After this presentation, if you have any lingering questions, feel free to contact me through that Google form, and I will get back to your query. So just keep the screen on for a minute so you guys can go on to Menti and enter the code so you guys can ask questions. All right, so that was menti.com, and then the code's 874430. Well, great. Questions are rolling in. What is the day-to-day experience of being a mechatronics engineer like? Well, like I mentioned before, a mechatronics engineer, you're working on both mechanical, electrical, software, and control systems. So one day you could be developing like some mechanical fixtures or specing on like a motor based on its mechanical performances. And then the other day you could be developing the software or firmware systems which control that system. And then you can also be working on the electronic side of things, like designing different circuits, using computer software to simulate it, or be working in a lab actually doing a bench testing. Or you could also be working out at a flight line, for example, testing drones or other aircraft. So it could be very variable, but definitely because it's multidisciplinary, you definitely get to be exposed to multiple disciplines of engineering at once. It's never a dull moment. I hope I answered this sufficiently. Why are there no electric planes? That's a great question. I assure you that electric planes are coming in one form or another. Keep on the lookout. In this coming years, within this decade, I'm very confident we'll be seeing a much larger ratio of hybridized aircraft or electric aircraft. And yeah, keep posted. Things will be happening in the coming years. Okay, but I guess to extend to this, for example, the battery technology you see in, for example, Tesla vehicles, it doesn't scale well for larger applications. For example, the energy requirements of a Tesla vehicle would be magnitudes of order smaller than, say, a 737 or another commercial aircraft. And to scale up in terms of, say, lithium-ion battery technology, it's just not feasible to have such a large aircraft powered completely by batteries. But other electric options are able to be pursued. Did you take any honors advanced courses in high school? If so, do you believe that they help prepare you for what you study in university? Do you believe that they're actually useful? Huh. Well, that's a great question. Well, I did take a few honors courses, maybe a few AP courses as well. They were definitely great in preparation for university, but at the same time, it would only help you, for example, in that first year. As courses and classes become more complex, perhaps lab-based for like engineering later on, they have less of an impact. I would recommend like if you can, like instead of taking or as a complement to these honors and advanced courses, perhaps take a drafting class, take like a technology education class, take some other trades class. So if you do choose to follow the engineer route, you'll have more of the practical skills and experiences to allow you to succeed. Can you explain more on common filters and how they work? Yes, I can. Let's go back. We will talk about common filtering. So with a common filter, we have, well, like I mentioned, we do have like predictive states, measurements, and optimal states. We're observing states at every time step or at every interval of the microcontroller. So, and we're building upon that collection of previous data. At the same time, we're taking a measurement of all the current sensors and instrumentation systems. And essentially, we're trying to average or to determine what ratio of data, of accurate data should we take from the sensors, how much data to take from the previous states. And then by some algorithm or some weighting algorithm, we can combine that data together so that we still have some optimal state. So for example, if you're measuring airspeed or velocity of the drone, you can use a GPS velocity, or you can use like velocity from the pitot tube. But in the event that one of them is inaccurate, you can have different weightings for them so that you can trust one sensor more than the other, so that you'll still have an ideal state that you estimated from a collection of live data and storage a history of previous data. I hope that explains it in sufficient depth for the purpose of this presentation. Can you describe more the application process you took to land your job or internship at Airbus? Okay, great. So I did mention before that you can start off with like an Arduino project. So I think that's quite important. You need to complement your academic work, your academic studies with personal projects. Like you can teach yourself like the skills and get the experience needed for some of these jobs, but you can't teach yourself the passion or the interest. So in order to, for example, to work at Airbus, obviously you have to have an interest in aircraft, but to complement that with hard skills, working on personal projects, like through a student design team, like a UBC UAS or an Arduino project that really makes you stand out from your peers. And for the particular application process to Airbus, I just applied online, but I had enough keywords and projects in my portfolio to enable me to have a competitive edge. What kind of student club should I join to boost my skills and knowledge for mechatronics, robotics in particular? Well, you can join a team like UBC Unmanned Aircraft Systems. You can join a student design team, which some teams at UBC, they focus on robots. I think there's like Thunderbots, and then there's also Subbots. I'm sure SFU has a comparable or relatable amount of clubs as well. If not, like I said, you can just do various personal projects. YouTube, Google, various forums have many different avenues which would allow you to develop these skills. So just search on Google good projects for robotics, or like Arduino robotics projects to complement what you can get from a student team. So yeah. How much time is given to probably develop and research the sensors on your Airbus project? Oh, because the purpose of the project was to move at a very rapid pace, the deadlines were definitely very ambitious. It did help having some previous knowledge of the sensors and instrumentation systems, so I could just extract that knowledge and then bring it over to that project. But if you want an exact time frame, it would probably be too long. So not much time is given, but you learn to adapt and to work quickly under various demands, prioritizing different tasks so that you choose or select like the best sensors given your constraints. I hope that answers the question. If not, please ask it again or rephrase it. Can I use a Raspberry Pi as a flight controller? Yes. Okay, well, you can't use a Raspberry, but you can use Raspberry Pi as a flight controller. There are a few flight controllers. I believe the Navio is based off of Raspberry Pi. I will remind you, however, a Raspberry Pi does have its own operating system. So whatever commands or the speed or like the quickness of things running on Raspberry Pi, it is somewhat constrained by all the peripherals around the Raspberry Pi itself, which is why something like the STM32 base microcontroller is used within the flight controller, which I showed in this presentation. So yes, you definitely can, but I don't think it's the most optimal solution. How should coursework impact your own time to develop your skills in mechatronics? Well, I don't think I've taken any independent courses or work, but I mentioned before, all the time I spent on the UAS student design team has been invaluable, designing like various electrical, like the telemetry systems on board the drone, developing scripts to do things in the background, gain experience working like within a laboratory or like a test bench environment. So yeah, if there's a student design team at your university, I would suggest you do that to get that practical experience. If not, you can also I can mention do various personal projects. The internet has a lot of those. Have you ever delved into ethical aspects, especially warfare? Well, yes, ethics is definitely a very important question here. I think that drones are cool. I don't necessarily have comment on what people use the drones for, but it's definitely an issue that is quite common. How do you know that decide on personal projects to work on? Well, my interest is in aircraft, aviation, drones. So my personal projects are focused on UAVs. However, if you think Tesla cars are cool, maybe you want to make your own project to develop a self-driving car, maybe based off a Raspberry Pi, maybe based on some OpenCV library in Python or MATLAB. So this is very interest dependent. Are concerned about job markets more than find topics they enjoy. Do you have any advice on priorities when choosing what field to enter? Wow, you guys are asking a really diverse range of questions. Well, I think someone once said, if you like your work, or if your passion interest is related to the work, you'll technically not be working, but you'll just be pursuing your hobbies or passions. So I think it really depends. It just depends on the person. But I think someone else also said that do something that you're good at or you're interested in, and then the money will come after. So it really depends. There's various answers to this, but it depends. Are UBC design teams exclusively for UBC students? I think for the most part, yes, because, for example, to get access to the workshops, the labs, or the equipment, it is paid for by UBC tuition and UBC donors. However, with, I believe there are different opportunities to engage and work with UBC design teams. And that question could be better posed to some of the team leads of those design teams. How much do you make per year? I make a humble living. I love today's session, but is it possible to receive a copy of the PowerPoint? Yes, I can make the link available for all of you guys. How long have you been doing mechanics? Well, if it meant mechatronics, I would say mechatronics would be when I started the mechatronics coursework and complementing it with the experience gained through co-ops and working at different jobs. I'd say several years so far, but I think this is a great field to go into, and you'll probably like it too. Is Python a good language to program in aircraft? No. So, for example, Python, even though it's really easy to code, that means that everything in the background supporting it is running in the background. So even though for the user, it's easy to code, in the background, it's perhaps taking more processing power, more memory than another programming language. So perhaps a slightly lower level one, like C++ or C, can be better. However, if you're not designing a perfectly optimized drone, if you're just wanting to do something to start out on, I think it's suitable. What's the job outlook for mechatronics engineers? Well, as a graduate from a mechatronics engineering program, I want to say very good. How is instrumental data converted to useful data in a feedback loop? Right, so this is part of the feedback. Let me go back into here. So all the instrumentation data comes inside the feedback loop. So for example, that little compass, the G_compass over there, that's the feedback that you're receiving from the aircraft sensors. And without this feedback loop, the drone doesn't know, for example, how much it deviated from its flight path. Well, it just wouldn't know because you have no way to sense. So your response would likely be something like this, where well, it would be very undesirable. Wait, whoops. I've checked out the job market, and quite a few of the engineering jobs require either mechanical, electrical, or software engineering specifically. How lucky have you found it to be noticed hired? Well, like I mentioned before, mechatronics engineering offers you a very nice foundation in mechanical, electrical, software, and controls engineering. So by having this degree, I would say that more doors are open for me because I'm able to do a job, for example, of what a mechanical engineer would do, working with like stresses, aeroelastics, torsion, heat, friction, thermodynamics, or working with like electrical systems, where it be through a microcontroller or through wiring harnesses or for wireless telemetry equipment, or software designing firmware or writing scripts for like computer vision algorithms. Having a mechatronics engineering degree allows you to pursue multiple more avenues. What inspired you to pursue mechatronics? Well, I think I liked airplanes, so I wanted to study mechanical engineering, perhaps go into aerospace. However, I also recognize that the technology, not only the vehicles, but the aircraft of today are becoming more and more digital and electronic and with like millions of lines of software code. And that's what drove me to pursue mechatronics engineering as opposed to say mechanical or aerospace engineering. And I'm sure this is relevant in many fields as well. What aspect of electronics is your favorite to work on? Well, my bias is towards instrumentation and electronics. I do think it's quite interesting to see to package a very nice circuit board onto a very small footprint, and then being able to convert like all the sensor data into something that you can read on your screen, and then you can draw conclusions from it. So I do like the electronics and instrumentation aspect of it. Can you explain what PID loop will look like in terms of code? Yes, I can. I have a snippet of the integral function. So we have the PID controller, and then this I block is something like this. You have the integrator, you're adding on or technically subtracting the error, and then you have some kind of scaling function, and then you have a delta time, which I think is the time elapsed, and then, or that could be DT, but regardless, this is something, this is what some of the code will look like that's actually low within the flight controller. You can find this all on the GitHub repo, which I posted in the resources link. Now, I haven't wrote a PID control algorithm for something as complicated or as complex as a drone, but with enough different, say, tutorials or coursework, you should be able to do it too. What do you work with? Oh yeah, for sure. So within the AlbatrossONE project, because it was aeroelastic project, work with a lot of aeroelastic loads and loads engineers, so mechanical engineers, working with, for example, data scientists who have a lot of experience handling, manipulating, drawing conclusions from large data sets. Also working with like some of the technicians inside the pro space, so I can quickly fabricate and produce some of the designs I made. So no, it's a very multidisciplinary. Having that mechatronics engineering background, it allows you to almost speak in the same language as many of the other engineers. How did you learn instrumentation side engineering? Were there specific courses where we were able to learn that infinitely? That's a great question. Well, I think starting off, like working on the UAS tune design team, that got me exposed to like accelerometers, gyroscopes, and inertial measurement units. And then the coursework actually followed, like was after that. So yes, there were instrumentation courses, learn more about sensors, noise rejection, learn about different Gaussian distributions and sensor like failure modes. But yeah, both through coursework and through practical aspects, like through student design teams, and also a lot of self-learning too. Google has a lot of information on it, and well, you just need the self-drive in order to learn on your own. Which school is better, UBC or SFU? Both offer competitive programs. We'll look out for when considering co-op for a company. What do companies expect from a co-op applicant? Well, I think that if you're going to work as a co-op, at the minimum, make sure that it's a paid position so that the company would value your time. Often I look on Glassdoor to see if a company has any reviews. And what do companies expect from a co-op applicant? Well, in terms of a co-op.
Hi, Raymond. I think you may have cut out in the last bit. We didn't quite catch your last answer to the questions.
Oh, sure. Are we still standing by to resolve the technical difficulties, or am I going to go through the questions?
Oh, you're good to finish.
I think you're good now. I think we've got it sorted out.
Oh, okay. Sure. Let me go back.
We're just going to take a couple more questions and then we'll have to wrap up the Q&A session.
Sure. Okay. I think Sophie also mentioned that you guys can share like the Google Forms link too. So I'll do my best to answer all the questions, perhaps better through Google Forms. Yeah, so computer science or mechatronics, the degree is just a piece of paper. It doesn't define who you are, where your experiences or interests lie in. So I think either, but if you do want to, for example, spend more time in front of a computer screen, hashing out different C code or whatnot, perhaps computer science. If you want to work with also hands-on, work with electrical systems and software and mechanical at the same time, perhaps mechatronics. At the same time, a few of my classmates, even though they graduate with a mechatronics engineering degrees, they're working in like a very heavy software field at a tech company right now. So it's quite variable, right? What are some projects a high school student can do? Arduino motor control project. There you go, 110 motor projects on this website. Find one of these. All right, how big is the market for mechatronics really? It's being covered really brown. What you can move into, how realistic is that? Well, yes, so the degree gives you the flexibility of pursuing something in a particular field, but at the same time, to make yourself stand out from different applicants, you go out on co-op, you have personal projects so that you can stand out and really be suited for that role that you're applying to. If I'm interested in the aerospace industry, is it better to say mechanical or mechatronics engineering for both general and electric aircraft? Well, I think I kind of touched upon this question before, but I understood that aircraft today are becoming more digital electric connected, which is why I chose mechatronics engineering. If you do want to focus more on aerodynamics, aeroelastics, or other more pure like aero aspects, perhaps mechanical engineering is a good bridge into like a master's in aerospace. Sorry, Irene, how much more time do you have? Do you want me to call off now, or are we going until 12:30?
We can take 2 more questions.
All right, 2 more questions. What do companies expect from a co-op applicant? I think I answered this. As to how mechatronics applies in other transportation systems like trains. Well, for example, trains like magnetic levitation trains, you're generating an electric field. You also always have like some form of like software controller. Like I said, like ships as well, they will all have like an autopilot system. They'll have like a mechanical system to propel themselves. So it's very applicable, and you can extend why presented into whatever mode of transportation you're looking for. All right, last question. What are your values as a mechatronics engineer? Well, I think a key skill or value that I really like for myself is my ability to self-learn. So if you're able to go on, for example, Google to solve your own problems, to deep dive into a particular subject field, even though it's outside your comfort zone, you'll be able to succeed well within a mechatronics engineering role. All right, and I believe this is the last question. If there's any questions which I didn't get around to answering, you can fill out the form and I will personally answer each one of them.
All right, thank you so much, Raymond. That was a very good question to end off on. And again, we'll be sending that form that Raymond mentioned to the chat so you guys have easy access to it. With that, I'll be passing it back to Sophie to wrap up the workshop.
Great, thank you, Irene. And thank you so much, Raymond, for your amazing workshop. And thank you everyone for joining us. This workshop would not be possible without you being with us today. SRIL is a rapidly growing youth organization specializing in robotics and STEM education. In 5 years, SRIL aims to be the center for innovation in BC. If you would like to take part in innovation projects or engage in STEM education and outreach, SRIL team applications open later this month. For more information, please go to our social media and website.
Finally, please fill out a short survey that will be sent into the chat. By attending all 3 workshops and completing all 3 surveys, you get a chance to win $180 in prizes. We look forward to seeing you soon and hope you join us in empowering youth to develop their innovative potential.
Thanks, everyone.